So in this module, we'll look at how we can represent voltages and currents in machines in terms of space vectors. And these space vectors are very compact notations, and moreover, they give us a very good physical interpretation as to how these machines operate in the first place, and later on, how we can control these machines using this space vector analysis. So let's start with this current space vector in the stator winding. And here, we have three individual windings with currents IA, IB, and IC. But we can create this stator current space vector represented with this arrow on the top here at any given instant of time by taking instantaneous phase currents and multiplying them with their axis orientations, like 0 degrees, 120, and 240, and then summing them up. So we get a combined current space vector, as you can see here, which has an amplitude in this complex expression, an amplitude, and a phase angle over here. And similarly, we can do for phase voltages. So it's very useful to at least get the physical interpretation of the current space vector. So to do that, we will multiply this current space vector definition we had in the previous slide with the number of turns which in each phase, that n sub s, by 2. So doing that gives us the MMF, as you can see from this first equation, the MMF associated with each of the phase windings, MMF that is impressed on each of the air gaps, and then when we sum them up, that gives us the combined stator MMF, as you can see here, F sub s. And so what we see that the stator current space vector is represented is related to the MMF space vector by this number of turns over 2 factor. And so similarly, the amplitude of the stator current space vector is related to the amplitude of the MMF space vector, and similarly, the angle at which this current space vector lies at any instant of time is the same as at which this MMF space vector would lie. So, what we are saying basically that these two are collinear, and of course, the flux density space vector is related to the stator current space vector over here. So the bottom line is that the magnetic field that is produced in the air gap is a combined effect of these three currents in phases A, B, and C. But equivalently speaking, we can say that we have a hypothetical winding, as shown on this figure on the right. And this hypothetical winding has sinusoidally distributed turns, n sub s, number of turns, and it has a current that is flowing, which has a value of is hat over here. So each turn has this current is hat, but the number of turns are sinusoidally distributed. And the MMF produced by such a hypothetical winding with this orientation that we see is the same as the currents produced by IA, IB, and IC flowing individually in these three phase windings. So this is very helpful in describing in calculating the torque expression, as we'll see. And here is, if just to show that BS and IS are collinear at any angle, and similarly here, BS and IS would be along this axis over here, right here. So, we saw that we could go from phase currents to the stator current space vector, but how about the other way around? Well, it is certainly we can do that if somebody gives us a current space vector. We can find what the individual currents are associated with these three windings. And this is made possible because we have a constraint here that the sum of these three currents by Kirchhoff's current law, IA plus IB plus IC is equal to 0. So making use of that, we can mathematically, graphically, as shown in the slide, we can find, given a current space vector, stereo current space vector, we can find what the components IA, IB, and IC would be. So what happens under balanced sinusoidal steady-state excitation? So let's say we have this three-phase winding in the machine, and right now we're just considering the, let's say, the magnetizing currents. The rotor is open circuit, electrically open circuited, and we have these three currents, IMA, IMB, and IMC, and they are sinusoidal. And arbitrarily, let's say that the time origin t equal to 0 is at an instant where the current in phase A is peaking, and its amplitude is Im hat here. So the question is, what happens to the stator current space vector defined in terms of these three phase currents? What we'll see that if we substitute for the stator current space vector these phase current components into it, we'll find that this stator current space vector has a constant amplitude, which is this here, and it rotates at a speed which we'll call synchronous speed, omega. And this omega is 2 pi times the frequency of these phase currents that we are applying here. So that's what this diagram in the middle, of course, is showing that these three currents are sinusoidal, and they are 120 degrees apart, and they have equal amplitude. And what we see on the right side of this diagram is that the stator current space vector is rotating at a synchronous speed, omega, which is 2 pi times the frequency. And so at time 0, it's along the phase A axis, because we chose the time origin to be at an instant where the current in phase A axis is peaking, but it is continuously rotating at a synchronous speed. So at, let's say, at 120 degrees, which is 2 pi over 3 radians later, it is the stereo current space vector is peaking along phase B axis, because at that instant of time, the current in phase B is at its positive maximum. So we can see that mathematically over here, and the bottom line is that we have a rotating MMF distribution in the air gap, and this flux density distribution is also rotating, and the amplitude of this distribution distributions is constant under sinusoidal steady state conditions, balanced conditions, and it is rotating at a synchronous speed omega. Now, we should be able to make a relationship between, under this balanced sinusoidal steady state excitation, between space vectors and phasors. So let's do that. And so again, defining the time origin to be when the current in phase A peaks, and let's say we are looking at some instant of time. Well, here, we could look at some instant of time where current has some other value, not the maximum value. So I sub A in time domain, as you can see, is given by this expression, where time could be anything. So in this case, what we have done is, in fact, at omega t equal to alpha is when the current is peaking. So the time origin is not chosen to be when the current in phase A is maximum. if I said that earlier, I was incorrect. Uh, it's somewhere other than maximum at time t equal to 0. But at omega t equal to alpha, as you can see from this diagram, the current in phase A peaks. So given this time domain expression for current I sub A, we can write a phasor expression which will be if using the peak value of this current as the amplitude of this phasor, Im hat, and the orientation would be minus alpha for the phasor representation, which is shown in the phasor diagram on the right-hand side. So what happens to the space vector? Well, we know that the space vector is, for one thing, it has a constant amplitude, but it peaks along, it will be along phase A axis when the current in phase A is at its maximum. That means having chosen the time origin as we did in this diagram, it will peak, it'll be along the phase A axis alpha degrees later. So at time t equal to 0, this stereo current space vector is alpha degrees behind, and that is what is shown in this diagram. And mathematically, we can see that the amplitude of the stereo current space vector is 3.5, no, not 3.5, 1.5 times, the 3 over 2 times the amplitude of each of the phase currents here. So that's the relationship between the amplitudes of the phase quantity and the combined space vector quantity. And the other thing we notice is that the orientation of the phase, the phasor associated with phase A is the same as the orientation of the space vector combining all three phases. So that is shown in this diagram here. So this orientation here is the same as this orientation over here. Okay. Now, we can also get at the voltages induced in the stereo winding, knowing that we have these three currents flowing in these three phases. In this case, rotor is open, so it's only the magnetizing currents. So, we can take the time origin anywhere, but let's say that it's at an instant when the phase voltage in phase A peaks. So if that's the case, this EMA would be at its, it will be horizontal, and under this condition, these three windings appear just purely as inductances. If you ignore the resistance of these windings, so you can see that we can, first of all, in this diagram in the middle here, we can represent all three voltage phasors for phases A, B, and C, and similarly the currents associated with them are 90 degrees behind, and again for all three phases. But taking this, we can go to the next step where we say that first of all, the equivalent circuit for this phasor diagram is shown over here, but we can also express these phase quantities by means of space vectors, and certainly at time t equal to 0, where the voltage in phase A is peaking, therefore the combined EMF space vector would be along the phase A axis as shown in this diagram here, and similarly the current space vector would be 90 degrees behind, and it will be with the same orientation as the phase current A over here, as we had seen in earlier slide. And we know that if L sub m is the magnetizing inductance, then the voltage induced in phase A is related to the derivative of current in phase A by this L sub m. So we can write such equations for all three phases, where if you just strictly talk about a two-pole machine, this can be generalized for p-pole machines. Of course, the magnetizing inductance can be calculated to be this expression, not that we need to necessarily calculate that for our purposes, but it is helpful to see the relationship between this magnetizing inductance and the number of turns, the length of the machine, the rotor, the air gap length, and all those things here. But given this magnetizing inductance, we can calculate the relationship or express the relationship between the induced voltage because we have these currents into these windings, and so this voltage induced related to the rate of change of the current in that phase. And so here this magnetizing inductance L sub m includes the mutual effect. So mutual inductance from coupling from phases B and C are included in phase A, and similarly in other cases. And we can also see from this space vector diagram is that the voltage space vector is leading the current space vector, as shown in this equation, by 90 degrees, and the relationship is given by omega L sub m, which will be a direct result of converting equations like this into a space vector equation shown over here. So it's a very compact notation, and we'll see how it could be extremely useful having this phasor representation for understanding these machines, calculating the torque expressions, and so on. So here is a simple example where we have three applied voltages, and again, rotor of the machine is electrically open circuited, and there's no permanent magnets or anything like that on the rotor. So it's basically an inductance for all practical purposes, ignoring the resistances of stereo windings. And we can calculate, given these phase voltages, what the voltage space vector will be. And then, using the expression in the previous slide, we can easily calculate what the stereo current space vector will be. And we can also individually calculate what the phase currents will be at any instant of time. And we can also calculate what the flux density space vector will be in this machine. So this brings us to the end of this module, where we have looked at the use of space vectors to describe voltages and currents, and we have given a physical interpretation of the current space vector and how we can calculate the components given a current space vectors in terms of individual phase currents, and we can also calculate what the induced EMF would be in these phase windings because of these currents, and then we saw the relationship between space vectors and phasors, and so it's a very useful way of looking at analyzing these machines and then later on controlling them.